welcome to my problem 4 week 7 video explainer. So in this problem we are going to have two speakers in two different scenarios with two different people, one being Janet, who is standing 3 meters from one speaker and 4 from the other, and then Brad is standing 6 from one and 4 from the other. So we're just going to approach these problems in two different steps. And it is also important to note that the people who are listening to the speakers notice that the sound level varies due to constructive and destructive interference as the pitch is increased. So in this first problem, or the first part, A, we are trying to find at what frequencies will Janet notice a maximum in sound intensity. So just quickly, drew Janet standing away from two different speakers. We were given that the speed of sound is 343 meters per second, and we can calculate the path difference based on the distances of the two speakers, which will ultimately help us find out the frequencies. So we know that due to that path difference, n times lambda is going to equal to 1. So that wave distance, lambda, is going to equal to 1 meter. So as we move on, we know that the frequency is equal to the speed of sound, or the velocity, over that wavelength lambda. So that's going to be 343 meters per second, which we've already given, over lambda, which we previously calculated with that path difference. So at that frequency, we will have 343 hertz. When n is 2, we find that lambda is going to equal to 1/2. So the frequency is going to equal to the speed of sound over 1/2, or 2 times that velocity, which is going to be 686 hertz. And we have noted a pattern for our frequency that for every increase in the path difference, that will also be proportional to the increase in the frequency. So that frequency for the nth term can be depicted by n times v. Moving on to the second part of the problem, we're going to use a similar approach, except this time we'll be dealing with different distances for the speakers, being 6 and 4 instead of 4 and 3. So how we previously calculated that path difference, we're going to find that it is 2 in this example, and n times lambda is going to equal to 2 instead of 1 from the first example. So that lambda wavelength is going to equal to 2 over n, as opposed to 1 over n in the first problem. So using the same methodology as the part A, we're going to find that the frequency is going to equal to v over 2n, and I didn't go through the specific harmonics just because there's a pattern that we can find here. So the frequency is going to equal to the speed of sound over that lambda value, and in this case it's going to be 2 over n. So and just after some simplification, we can find that the n times the speed of sound over 2 is going to be equal to our frequency in every single harmonic that we're trying to calculate. So just some of the tricky problems, I guess, were just trying to find what value we could use for that lambda value as it changed in the first and second parts. So that was the main tricky part, and this just relates to what we were doing in class in regards to superposition, wavelengths, harmonics, calculating frequencies, and yeah, thank you.